So good day guys, let's solve a question on the principle of dimensional homogeneity using dimensional analysis. Of course, the concept is easy. We said that one of the applications of what while we're looking into dimensional analysis is what to check the correctness or to establish a physical quantity or equation. More of like to in case of when you have variations, you can find a constant and establish a relationship. That's one of the applications. So in today's course, we're going to be talking on what a sample problem that involves dimensional analysis. Now, to read out this question, quietly listen. The frequency of a stress string depends on the length of the string, the tension of the string, and the mass per length of the string. Establish a relationship for what? For the frequency using what? The concept of what? Dimensional analysis. So therefore, we are having a case where they say the frequency of a stress string depends on what? The length of that string. Also, it depends on what? The tension in the string, and also depends on what? The mass per unit length of that string. So you can say this is equation 1, equation 2, equation 3. Combining all these variations, combining the equations, we have that the frequency is direct proportional to what? The length. So let's put this in brackets. Also direct proportional to what? The tension. And lastly, the mass per unit length of that string. Of course, take note. Let us represent the mass per unit length as mu. So let's represent this as mu. So we have a case where we say the frequency is directional to what? The length, the tension, and mu. Let's call this equation 1. Of course, in the case where we have a variation sign, we're going to introduce the equality sign. In that case, we also what? Bring about the constant. So let's call that constant k. So we're having a case where the frequency is equal to what? The constant k, the length of the string, the tension, and what? The mass per unit length. This is what dimensional analysis is. So let's call it equation 2. Very important. Now there's a concept I should tell you about dimensional analysis that is very, very important. That concept is very, very important to you, and please listen. Of course, frequency, you should know that we said that we stated the principle of dimensional analysis as what? A case where the dimension of what? The physical quantities are what? Identical and equal at both sides of what? The equation, right? That's what we stated as the principle of dimensional analysis or homogeneity. Now, in this case, we're going to express the frequency in terms of what? Its dimension, and we're going to express all of them in terms of their dimension. But before we do that, we're going to assign powers for each of what? The variables. So in this case, we're going to assign a alphabetical letter to what? The dependent variations, which is more like the length, the tension, and what? In terms, which is we have expressed this as mu. So doing that, we're going to assign that. So we have k, we have length. Let's assign length as x. We have tension. Let's assign tension as y, and we have mu. Let's assign mu as z. So that's the concept of dimensional analysis. Now, when we have done that, we have that the next step is what? We're going to bring this in this dimensional analysis. Break this to dimensional analysis. So now take note. Frequency frequency is number of oscillation over time, right? Which is expressed as what? T raised to the negative 1. But take note, we are going to express this frequency in terms of what? M0, L0, T negative 1. Because of other parameters are going to be expressed in terms of what? MLT. So therefore, M raised to the power 0 is 1, L raised to the power 0 is 1. So therefore, this is also the same as what? This. So that's the principle we are going to do. We are going to break down all the parameters of physical quantities in this equation to its fundamental units. So doing that, we have that, of course, breaking frequency, we have frequency as what? So let's bring this down. Breaking that, we have the frequency as M0, L0, T, negative 1. So equal to what? K. Of course, K is a constant. We did not assign any parameters to that, meaning that we're not working with K. So of course, length, which is normal L, so we have length we have L raised to the power x. The next one is tension. So we have tension as what? Tension is a force, right? So we have force as M L T -2. We are assigning this as what? Y. Now the next is what? Mu, which is mass over length. Mass over length is M L -1. So we assign this as what? M L -1. So we have raised to the power Z. So the next step is to collect like terms. So knowing we have this at we're still going to work with this. We are creating this to K. Now we're going to take like terms. We're having M multiplying Y, which is becomes M. So first of all, let's open the bracket first. We have LX, we have M multiplied by MY. When this opens, you have LY. When this opens, you have T -2Y. This opens, we have MZ, L -Z, and what? Okay, nothing is left. So that's the concept. We're going to collect like terms here. So we equate this, we have this. We have K. Of course, we're working with M first in the same order, but trying to make this look like what we have at the left hand side. But now we have M, and M from indices, we have the same what? Base and different power. So we can express it in terms of what? M raised to the power Y plus Z. Of course, everybody knows this in indices. So the next term is L. We're working with L next. We have L. L is in terms of X and Y, and also -Z. So we have X plus, of course, the next one is what? Y negative what? Z. Last but not the least is the time. So we have T. Of course, what do we have here as T? -2Y. So we have -2Y. So that's the concept of dimensional analysis. So let's continue on that other side of the board. M0 F0 T -1 equal to what? K. We have M. Of course, we have M Y plus Z. We have L X plus Y -Z. We have T -2Y. So now the next step is we are going to what? Consider M, and we're going to equate more of like taking M and M. So we have for M. So considering for M, we have that M raised to the power 0. We are considering M now. So we're taking this and we're taking everything we have here is equals to what? M raised to the power Y plus Z. Of course, this will cancel this, and we're having 0 is equals to what? Y plus Z. So therefore we can see that Y is equals to what? Negative of Z. So take note of this concept. So let's consider for L. So we're having for L, we're considering L raised to the power 0 and L raised to the power X plus Y negative Z. So we're having L raised to the power 0 is equals to what? L, of course, we have this. So this will cancel this, and you have, and we have 0 is equal to what? X plus Y negative Z. But we know that Y and Z are the negative of both, so we can represent Y as negative Z. So when we do that, we have that 0 is equals to what? X. Of course, we said that Y is negative Z. So we're having negative Z, which equals negative 2Z. So therefore, we can have that X is equal to what? 2Z. So that's the concept. So now let's consider for T. So we have for T, which is T -1 is equal to what? T -2Y. T will cancel T. Negative will cancel negative. We have the 1 is equals to 2Y. Divide both sides by 2, and we have Y is equals to what? 1 over 2. So we said that Y is equals to 1 over 2. We also said that Y is equals to negative Z. So therefore Z is the negative of what? Y, which is negative 1 over 2. And we also said that X is what? 2Z. So therefore, anywhere you see X represented as 2Z, which is the same thing as the 2. Of course, Z is negative 1 over 2 multiplied by negative 1 over 2. This will cancel this, and it becomes negative 1. So therefore, we said that. So therefore, let's have X as what? Negative 1. We have Y as what? 1 over 2. And we have Z as what? Negative 1 over 2. So therefore, we're going to substitute these values into what we have as our expression here. So we're going to wipe from here up. So we're going to only retain what we have as this expression. Very important. So therefore, knowing that x is equal to -1, y is equal to 1 over 2, and z is equal to -1 over 2, we are going to substitute into this equation. Of course, we had that earlier, that the frequency is equal to what? K L X. Of course, we have T, Y, and we have the mu Z. So therefore, substituting X, Y, and Z, we have that the frequency is K L. So X is -1. So we have -1 here. We have the tension Y as 1 over 2, and we have mu, which is M over L. We have it as what? -1 over 2. So therefore, let's play with this. We have that the frequency is equal to K. So this is -1, meaning it's going to come down. So having a case where it comes down to L, we have T. This is T raised to power 1 over 2. We have mu -1 over 2. It's going to come down. It's going to be mu 1 over 2. Of course, we're going to combine these two because they have the same power. We have the K over L, T over what? Mu raised to power 1 over 2. So we have this as what? K over L. But 1 over 2 is something as taking the square root of what? T over mu. So the concept is very easy. We can say that our frequency, or the formula, which is an established relationship, is equals to what? The constant K over L, the square root of what? Tension over what? Mu. So we can decide to express this as what? The mass over length. Of course, we say that mu is what? Mass over length. So we can decide to write it that way, which is K over L is the same as what? The square root of what? Now mu is mass over L, mass over length. That means the length will come up and the mass will go down. So it becomes what? The tension multiplied by the length over what? The mass. You can decide to bring this out and express it in terms of this, or I would like to stop here. So this is the concept of what? Dimensional analysis of dimensional homogeneity. The concept is very easy. We're going to solve next problem on this topic.